What's up? This is Physics 2212 Lab 3 Circuits. This is just a quick little table of contents. We're going to talk about the introduction, some physics principles, series circuit, RC circuit, assumption, source of error, discussion questions, and the conclusion. So the introduction for this lab is just, the purpose is that we're going to observe and predict how a circuit acts based on batteries, resistors, and capacitors in series and parallel with a real circuit. And then we're going to use multimeters to measure the current and potential circuit and compare to some calculated numbers, and then examine the behavior of ohmic resistors and capacitors. We have some physics principles we're going to go over, but the final outcome that we're going to look at is going to just be these are going to be some of our potential differences and the current of the circuit. So the physics principles for this one, a node rule, which says the current going into a node must be equal to the current flowing out of the node. So I1 and I2 have to equal I3 in this example, or I2 plus I1 plus I2. So for loop rule, it's all electric potential differences in a loop must add to zero. So in this case, this loop has to be zero, whole thing has to be zero. So it's in class. And then for Ohm's law, we just have V equals IR, which we're going to use later with current and resistance. So this was our first circuit that we had to make, the series circuit. This is the diagram of it. That's what was in it. So for the results, so we found the current in I1 and I2 to be 0.02 amps. And the reversed, when we reversed the multimeter, we got the negative version of that because we're just measuring it backwards. So when we changed it to voltmeter, we got minus 2 volts and 0 amps because when you use this voltmeter, it breaks the circuit, which means it doesn't close anymore. There is no more current. The potential difference, so the battery is 3 because 1.5 each, and these are our measured values that we measured. So when we sum this, we actually had 0.11, which is very close to 0, but as we'll see later, some resistance causes this to be different thanks to ammeters. And then we checked it across the 100 resistor, and we got 0.01 amps. And then when we made it parallel, it actually increased 0.2 amps because current increases because the electrons had a lower R path to take because they could go through the ammeter. And then the resistance of the components, we were given this equation dV, which is our potential difference, over the current is equal to the resistance. So the total is going to be 150, but we know the wire has none. These numbers are based on our potential difference divided by the current, so there we go. And then the ammeter is just equal to the total minus these two values. This is our graph analysis. So as we can see, it starts at the battery, it goes up 1.5. Next battery goes up to 1.5, so we're at 3. When we hit the first resistor, we go down to 2 because the first one should roughly decrease by that much, or decreases 0.92. And the next one, we hit the 100, it decreases all the way back down to 0, which makes sense because of the loop rule. And then the reason the ammeter doesn't change things when you're measuring it for volts is because the resistance is negligible in that case. So then we have the RC circuit, which is where we use light bulbs and a capacitor. So when we first used a battery and capacitor, it became bright and then became dimmer. Same thing with the normal capacitor, but it seemed like it dimmed a little bit faster, right? And then we repeated with our other bulb, so we used a 10 ohm for this one. Then we used a 21. It changed a little bit because of the resistance differences. So then when we actually measured these times, when you have the 20 ohm bulb, and it took about a minute 20 seconds with the battery and capacitor. But with just the capacitor, it took only about a minute. And that makes sense when we look at these equations, right? Because the battery is actively charging the capacitor, which is also powering the bulb. So you're kind of getting this replenishment there. But when you don't have that, it's just the capacitor energies that was stored. So there's no increase, it's only decreasing without the battery. So it makes sense that this time is lower than that time. Some assumptions we made are that the battery is fully charged and that resistance of the wire length is negligible. And then there's some errors, just human error, using the stopwatch correctly, loss of charge due to external inputs, something might have been charged in the room, and then inaccurate measurements from the multimeter. So the discussion question for this was, if you charge the capacitor with no resistor, what would kind of happen? So in an ideal model, the capacitor would be charged almost instantaneously because the current would just flow straight to the capacitor charging it. However, in real life, this is not the case because batteries and ammeters actually do have resistance in them, right? So the measured time took slightly longer, that being just several seconds. So not like insane longer, but still there is a noticeable difference there. So in conclusion, when we use our knowledge of circuits and physics, we can calculate and find the current potential differences and resistance. Certain rules, such as the node rule and loop rule, along with the equations for Ohm's law, let us make predictions. Multimeters give us information, and allows us to measure things. Capacitor interactions with batteries and outputs can change the way things operate. One thing I did just want to say, I'll go back over here. This is our first circuit, and also so the system is going to be the circuit, and the surroundings is going to be everything else. So that's it for this video.